All right. So we were talking about. I actually brought the last two slides, and just to refresh your memories that what we were talking about. We were talking about motion on a curvilinear path. We talked about motion on a straight line. Then we went through a couple of examples. Now we were talking about motion on a curvilinear path, and we said we're going to use different types of coordinates. Like, to be exact, three types of coordinate systems. They're going to use three. I would say three coordinate systems. Now, the first type would be Cartesian coordinates that we talked about. That pretty straightforward. You have a Cartesian coordinate system x, y, z, with unit vectors I, j, k along those axes, and then we define the position of a point or a particle. Took derivative with respect to time. We got the definition for velocity and definition for acceleration. And we said those definitions basically they have three components each: position, velocity, acceleration. Each of them has three components. One in x direction, one in y direction, one in z direction. Then we used this basically basic definitions for position, velocity, and acceleration in Cartesian coordinate system to look at a specific kind of problem, a specific kind of motion, projectile motion, right? Projectile motion, we said, well, imagine that you throw a stone or you throw some object, right? And in our case, we're going to restrict everything into a two-dimensional motion, like xy plane, xz plane, y z plane, depending on which plane you want to use for to describe your motion, but it's always in two-dimensional space. In this case, we used xy coordinate system, and we said following the definition of acceleration, velocity, and position for motion on a curvilinear path, right? It's not a straight line motion, right? Well, if you think about throwing something, it goes up and it comes back down, right? Obviously because of gravity. And the assumption we made was that we only give it some initial velocity, and we know the initial velocity, or we identify the initial velocity with v naught and identify the angle that that initial velocity creates or makes with horizontal line with theta naught. And then following definition for acceleration, we could find the components of velocity in xy coordinate in x and y direction, and using definition for velocity, we could find components of position x, y. Using these, we can exactly say at any given moment, provided that we have enough information about the problem, we can say where the particle is or where the object is, where the point is in this plane, and how fast it's moving, right? Knowing its x and vx and vy components of velocity in x and y directions. Right? It's just a vector. So velocity is a vector. Knowing that the x and y component, you can pretty much know everything about it. Same story about position. Right? If you know x and y, you know where the particle is at any given moment. All right. So let's take a look at a couple of examples for projectile problem, and we'll take it from there. All right. So first example, pretty straightforward, I think. We have a projectile. Well, let's see. It says a projectile is launched. Yeah. Projectile is launched from the ground level with initial my handwriting could be a little better. Ground level with initial the initial velocity uh, 20 meter per second. 20 meter per second. That's pretty much it. Determine its range R if theta naught is equal to 30 degrees. So here is what we are given. It says we have pretty much XY coordinates like this. And that projectile is thrown, let's say, from the origin here. This is coming as part of the problem with V naught. And this is theta naught. And it follows this path, something like this, and it hits the ground at some point. This is R, the range that we're looking for. All right, so it's again, it's a pretty straightforward problem, just to see how can we use those equations that we just introduced. So things we know here, we know, or let's keep this, I'll change this. We know initial velocity, right, we're given is 20 meters per second. And we know initial angle, right? The angle that initial velocity creates with our ground, with the ground. So 30 degrees. These are the things we know. All right, let's see. We're asked to find this R range, right? Go back to the equations we have. Which one is going to give us the range here? So we have components for velocity. Well, not really is the range we want. And we have components for X and Y, right? Second one, yes, exactly. Thank you, Sam. So X, pretty much X gives you where you are at any given time, right? We said X component tells us where we are at any given time on X axis or in horizontal direction. So in this case, we want to know at the end of the motion, where do we land, or where does this projectile land? So that R is pretty much our X. So let me write it this way. I can, so I'll say X is equal to R, or maybe the other way around. R is equal to X is equal to V naught cosine theta naught T, and plus, let's say, X naught. In this case, X naught is, what is X naught in this case? Given the coordinate system, 0, exactly. So this would be 0. Right. This gives me V naught, which is 20 cosine 30 degrees T. Here's the problem. In order to know R, exactly, it's there. In order to know R, right, I need to know at which time this projectile hits the ground. You know, how long does it take for this to get from the beginning of the motion till the time that it hits the ground again? So it goes from ground, comes back to the ground. All right, based on what is given the coordinate system. So how do I find that T then? Well, if I don't have T, I can't find R. I'll go back to what we have. Now, given the information we have, right, the Vy, we have Vy. We can use, well, we don't know what is Vy, right? But we can use the last equation, this one right here, y. which basically says y equals to minus 1 over 2 gt squared plus v naught sine theta naught t plus y naught. Now, what do we know is that we know that this particle, this object, is starting from the ground, y equals to 0, and it ends up being on the ground. Like y naught is equal to 0 and ends up being on the ground, y is equal to 0. So y naught is where we are in the y-axis at the beginning of the motion, y is where we are at any given time, right, on y-axis. If I know these two, I know v naught, I know sine, I know theta naught, I know g. The only missing part in that equation is t. So this is what I'm trying to say. If I use y is equal to minus 1 over 2 gt squared plus v naught sine theta naught t plus y naught. Now the motion starts from the ground, ends on the ground. So this y is 0 and y naught is also 0. Starting from the ground, y naught is 0. Ending up on the ground, y is equal to 0. So what is left is 1 over 2 gt squared. I moved it this to the other side. V naught sine theta naught t. You get rid of t values on both sides. You will get 1 over 2 gt is equal to V naught sine theta naught. And you pretty much have everything here. The only missing piece is t. So this t would be the t for the whole motion from the ground coming back to the ground. So that becomes 2 v naught sine theta naught divided by g. This is your t, right? We started from this equation right here. And we said we want to find the range. Now, the missing part was t. We didn't know how long does it take to complete this motion. We use the second equation for y direction. We have enough information to plug in and get the time for the whole motion from that equation. Once you know time, you can just plug it back to the first equation and find your range. We'll just plug it back. So let's put it this way. 1 becomes x, or r, is equal to 20 cosine 30 degrees multiplied by, that t would be t times v naught is 20 meters per second, sine 30 degrees divided by 9.81. Just feel free to take g 9.81 pretty much always. All right, so you do the math, you'll find the range. All right, I should have the value somewhere. So if everything went right here, we should have 35.31 meters. Well, I got rid of both t's. One t from this side, from right here. This t and this t. I can't. They just basically canceled out. So only one t was left on the left side. Right. Since y and y naught were 0, pretty much I moved this the 1 over 2 gt squared to the other side and canceled out one t from this side. All right. Question on this one. Nice. All right, so we looked at the range. We wanted to find the range. We didn't know the time. We went back, used the other equation, used equation for y to find the time t, because we had enough information. Remember, the information comes from the problem statement, right? If you look at here, it says the projectile is launched from the ground level, right? So we know it starts from the ground level, and we know right here that it goes from the ground, comes back to the ground. So y naught and y basically 0. All right, no question on this. Let's do another example. Let's go with, let's keep this as is. I'll change this example. This one says we have, or let me just go with the problem statement. A pilot wants to drop survey markers at some area. If he flies at a constant velocity, v naught is equal to 40 meter per second at altitude h is equal to 30 meters, and the marker is released with 0 velocity relative to the plane, let's see, what does it say here? To the plane, that was a very long if, comma, that's a little distorted. We have weird sentencing. Now it's asking at which horizontal D, I'll draw it in a minute, D from the desired impact point should the marker be released. Okay, so weird sentencing, but here is the situation. We have X, well, not exactly X and Y. We are not given X and Y. It's just the ground. So this is the ground. And let's just try it. Imagine that this is a plane. I will do my best to draw something as close as possible to a plane. Let's say these are the wings. Yeah, best I can do. So this is going with the velocity v naught. The height here is, this height is, if I can draw better, this height is h. Now if you take this as where the point that the marker is released, then this is what this problem is trying to ask. This distance d, let's say the marker goes in this type of motion, projectile motion. All right, so here's the problem, right? The plane is moving with the velocity v naught, right? If it flies at a constant velocity called v naught, it's constant, so at any given time, it's in x direction is 40 meters per second, meaning that even at initial moment is 40 meters per second. Altitude h is 30 meters, right? These are given. This is v and this is h. Now, another piece of information we're given is that the markers are released. So there is no velocity difference between the marker and the plane at the moment that these markers are released. So at the moment when they release the markers, the marker has the same velocity as the plane. Now the question is, if they want to, if the plan is to make sure this marker gets into this point right here at distance d, we know where we are, like where the plane. We want to know the distance d at which the plane should release this marker to make sure it hits exactly the point, this point right here. So distance d would be how far the plane should be horizontally or on x-axis or on the ground, basically, from the point when it releases that marker to make sure the marker hits that specific point. Right? A lot of assumptions are going there, obviously. In the real situation, it's going to be way off. There's wind, friction, or let's say air resistance. There is a lot of things are happening. The fact that the velocity is, anyway, it's an ideal case. Let's put it this way. So what do we do here? Right? It's still a projectile motion. Right? We still have some. We are in XY plane. Right? I'm going to take this as x. And take this as y. Could you take it here, like attached to this part, and take this as x and take this as y? Yes, you could. Well, I'm going to take the what we have at the bottom. The difference would be your y would be positive or negative. But I'll stick to what is at the. I'll stick to orange coordinate system. Right, that's what I take as my coordinate system. All right. So what do we do? Going back to the equations we derived for a projectile motion or a projectile. We want to find d. All right, just first d. What is d? Right, which equation or expression here we should use as an attempt to find d? Yes, x. We have to use equation for x, but Craig, you're right. It's the same story as the previous problem, right? We have to solve for time first because let's do it this way. So we go with x. Let's say this is x, which is our d, right? Would be v naught cosine theta naught t. Just double check if I use the right notation. V naught cosine theta t plus x naught. So what are the parameters here? What do I know? What I don't know? What are the things that I know? What are the things I don't know based on this coordinate system and everything? What is, well, V naught I know, right? V naught is 40 meters per second. What is theta naught? Do I know it? What is the value if I know it? Yes, exactly. So it would be 0, right? To see that, if you think about this plane moving this way, at the moment we drop that, so think about the marker. Like marker has this velocity at the beginning of the motion, and then it starts basically going down on a curvilinear path. So at the beginning of the motion, theta is 0, right? There is this is v naught, and this is exactly where it's released. Right? We don't really have something like this anymore. It's not going up. It's basically just going straight, v naught. So this theta naught that we define as the angle for v naught right there, and the x-axis or horizontal line becomes 0, right? Or in this case it's 0. So this is 0. What do we have for x naught? Well, I mean, we put the coordinate exactly where the motion starts for a marker, so that x naught becomes 0 as well. You could put it somewhere else, but then the problem is you don't have enough information. I don't want to confuse you, but you could basically put x, y coordinate here as well, right? You could put x and y here, and then say, well, x naught is minus d, and x is 0. Since I put the coordinate on the orange basically spot, or use the orange coordinate, x would be how far we're going to end up being from the coordinate system, which is x, and x naught would be 0. If you didn't follow what I just said, that's fine. Don't be too worried about it. So this is 0 because the motion starts right here, and the x component for the position is 0. Now, I just said depending on where you put the coordinate system, x and x naught can be switched. If you put the coordinate system all the way where it hits the ground, your x naught would be minus d, the initial position. Your x, the final position, because your marker ends up being exactly in the coordinate system, would be 0. But it's the same thing. You just move that number to the left and it becomes positive. All right, so here is what we have. We get 40, well, cosine 0 is 1, so we get 40 t. All right, now, as Craig mentioned, right, similar to what we did in the previous problem, now we have to find time. So in order to find time, we'll go back to the same equation that we used for this example, right? We said, well, we know where the motion starts, initial height. We know where it ends, final height in this coordinate system. So we can use that to find the time that takes for this motion to happen. So y is equal to minus 1 over gt squared plus v naught sine theta naught t plus y naught. Let's take a look. Start from y. What is y? Y is 0, right? Exactly. So where the marker is at the end of the motion, or if I take xy coordinate as the way I put on the this graph or diagram, this becomes 0. Well, minus 1 over gt squared plus t is what we want to find. V naught, we already know it's 40. Theta naught, it's the same story, is 0. And what is y naught? 30, exactly. Thank you. It is h, which becomes 30. So it's h, and h is 30. So this becomes eventually 0 is equal to minus 1 over gt squared plus 30. From there you can find time. Time goes to the other side. This becomes 2 times 30 divided by g, which is 9.81. So this gives you the time. I do have the value here. Time is we got 230 is 2.47 seconds. So this is the time that it takes for the this is the time required for the whole motion. Once you know the time, same story. If I just put 1 here from yes, this is t squared, so I have to either put t squared or I put this. You're right, Dylan. There you go. Thank you. So from 1, you'll get d as 40 times 2.47. Right. That number, at least what I have, is 98.9 meters. There you go. Here's what you get. All right, any question on this? Very similar to the previous one. The only thing that changes is that y and y naught are not zero at the same time. Y is 0 at the end of the motion, y naught, depending the way we took the coordinate system, y naught becomes h, the height, initial height, which is 30. All right, let's do one more example. I have a couple of sample problems for this section too. I'll just upload that. But let's do the next example as well in the class. Then we'll do. All right. So, if no question from this, let's go to the next one. So this example, it's a little different. Just the surface is a little tilted. So just wanted to see that. So projectile is released at 10 meter per second. Well, let's put it this way: is launched. Doesn't make sense. Is released. Is launched at 10 meter per second from a sloping surface the angle alpha is equal to 80 degrees. Find the range R. So here is the I would say situation, right? We have some angled, like tilted surface like this. See if I can make it a little better. No. All right. We have our projectile. It's, let's say, it's launched from here with some initial velocity v naught. And this is angle alpha. That's given in the problem. This is alpha, and this angle here is 30 degrees. Definitely things are not into scale. So what happens is that this goes from, let's see if I can rearrange this. Let's use this. This goes like this, right? Something along this line. This is the projectile. And this distance is all. This is the range you're trying to find. All right. So what do we do there, right? The difference is now the surface is a little not straight or horizontal. The story is pretty much the same. Few things change, like not few things. The only thing that changes is that the initial angle that you have and where you end up being basically in that coordinate system. Let's put the coordinate system here. I'll use a red so it's more obvious where it is. Let's put it, this one as x, and this one as y. It's supposed to be straight. So let's start from what we can see what we can do. So x, same story. R, we want to find, well, now we are in two-dimensional. Like, well, we are always in two-dimensional. We have x, y. Now it starts from the origin, goes all the way, but what happens is that where it lands is not exactly on the x-axis. Where it lands is somewhere in two-dimensional space, somewhere in y negative. I'm talking about this point right here, right? Where it lands. Goes down, so y is negative and some x value for that. So we have to find both x and y to locate exactly where that r is. What I do is that let's start with definitions. Let's just see if things are a little easier to follow. We said ax, well, if you remember how did we derive the equations, we said ax is 0 in a projectile motion, and ay is minus g. And I started from the fact that, well, when ax is equal 0, dvx dt is 0. That's ax, definition of ax. And vx became constant, and it becomes whatever it is at the beginning of the motion. I don't know if it's going to make it more confusing or more clear. I'm just following what I did to derive the equations. If you don't feel comfortable with that, you can just get the equations from what we had. Vx is v naught cosine theta naught, right? If you go back to the equations we derived, Vx is v naught cosine theta naught. Maybe I moved fast. Here is the first equation right here. Vx is v naught cosine theta naught. Maybe it's better if I don't derive it and I use what we had from before. So v naught cosine theta naught. What are these values? Well, v naught is given, right? Is 10 meters per second. What is theta naught in this case? Remember, what was the definition of theta naught? Theta naught was the angle that the initial velocity creates, initial velocity vector creates with the x-axis. So what is theta naught in this case? 50 degrees, exactly, Elizabeth and Bobby. Oh, Richard is there. All right. How do we get that 50? Well, look at the angle right here. This angle that V naught creates, I'm just going to draw it again here so it's not crowded there. This is V naught. This is your theta naught. Okay, theta naught is your alpha, the whole angle that you have, minus this 30 degrees. If this angle is 30 degrees, this angle here is also 30 degrees. This is 30. So it becomes alpha minus 30 degrees. A little bit of geometry there. So 80 minus 30. So it becomes 10 cosine 50 degrees. I'm just going to keep it here. This is Vx. We want to find the range. So you might ask, why did I start even from there? I could just go back, but what the reason I started there, well, probably we may not have even needed that. Let's just start from the same process we did from before. I guess it's easier. So x, remember, we want to find where this projectile ends up being. So we need x component in this coordinate, right? If this is x and this is y, let's say we ends up being here. This point, in order to identify where this point is, we need its y. If I call it p, yp, and xp. So we can say exactly what this R is. This is R. So we have to find X and Y. So let's start with X. I probably should have started with X. X is equal to, again, the equation we have for X. Nothing new. If you go back right here, X is V naught cosine theta naught T plus X naught. So I'll just plug that here. X is V naught cosine theta naught T plus X naught. Now the components, V naught, we already know. V naught is 10. Cosine theta naught, I talked about theta naught right there, so it's still 50, cosine 50. And we have T. X naught is 0 because I put the coordinate where the motion is started, so there is no X naught. We call this XP following the notations I put here. Let's say this is XP and this is YP, where the particle is. So this is your XP. I'll just put it separately, 10 cosine 50T. Now I have to find the YP, right? Where Y is. Just writing it here. We'll see what we are missing and what do we need. GT squared plus V naught sine theta naught, I believe it was T plus Y naught. So hopefully everybody agrees that Y naught is 0. Same story as X naught. Because we start from where the origin of this coordinate system is. Now let's see what do we have there. Only thing I know is 1 over 2g is 9.81 t squared plus v naught is t 10 sine, right? Same story, 50 t. This is the same. This is the next equation I got. So I don't know a lot of things here, right? I don't know XP is 10 cosine 50 t. Well, I don't know t. As a result, I can't find XP. YP, right? I don't know YP and I don't know t. Right? So neither of these I can find. It's not like before that start from 0, end up being 0. I have 1, 2, I would say 3, 4 unknowns. I don't know XP. I know it's a function of time. I don't know YP. I know, and I don't know T. So 3 unknowns, I would say. It's my bad. How do I fix this? I have 2 equations, 3 unknowns. Right? How do I deal with this situation? It's not like before that Y equation was giving me the time. Right now, I don't. YP, or where the point or particle is at the end of the motion, is not clearly specified. And I'm trying to find range R. The thing is, I can go with Vy, but then what does that give me, right? Vy would be minus GT V naught sine 50, and we don't know Vy, we don't know time there, and we also don't know, yeah, exactly. So 2 unknowns is still there. I can add, that's going to give me another equation, but it's going to also add 2 more unknowns. Here is the trick. Not the trick, but we have 2 equations, 3 unknowns, right? We have these 2 XP and YP. We don't know XP, we don't know YP, we don't know time. But the thing is, XP and YP are related to each other using R. We know that XP, look at this situation here. This is 30 degrees. Always triangles. That's always what helps us. So XP, if you look at this triangle right there, or XP or P, right, this triangle right there, how can we write XP as a function of R? So we can write that, right? Exactly, we can write that. It's going to give you the same thing that I'm trying to get to, but might be a little longer. XP squared plus YP squared is R squared. That's true. But we can do a little, exactly, Richard. So that's what I was trying to get to. Math is right. We can do that too. But the easier way would be just write XP and YP both based on R. So XP would be R cosine 30 degrees. And YP would be minus R sine 30 degrees. Hopefully everybody sees that. If this is my triangle right there, and this is 30 degrees, this is XP, this is YP, and this is R. So I write XP and YP as a function of R. If I do that, the first equation becomes R cosine 30 degrees is equal to 10 cosine 50t, and the second one becomes minus R sine 30 degrees is equal to minus 1 over 2 9.81 t squared plus v naught. Oh, I have v naught. This becomes 10 sine 50t. Right. So you have to do a little bit of calculation right here, but the bottom line is now you have two equations, two unknowns. Two equations, two unknowns. Mathematically, good enough. You can find the t from the first equation, plug it into the second equation, and solve it for r. Or we can find r. We can find r from the first equation, plug it into second equation, and find t. But by the end of the day, a little bit of plugging in and solving for those unknowns, you can find r and t now. So if you do that, r would be 17.21 meters, and t would be 2.32 seconds. These are your final answers. Well, you don't really need t. You're not asked to find t, so you're asked to find r, right? So a little more advanced compared to what we're doing from ground to the ground. We're going from ground to the ground, but the second spot that the projectile hits is not exactly on x-axis, and the range is not just x. Range is a vector, or no, the position vector, better to say, wherever the point is at the end of the motion. You need both x and y. You need to find both. What we did is that we just used a little bit of mathematics. We said, well, r is what is connecting these two x and y. Yes, exactly. So it's negative just because it's going downward. Right? I put yp here as negative because I'm writing everything in this coordinate system xy. Right? Xp is positive, it's in positive direction. Yp is negative because it's down. It's below where the origin is, and it's on the negative side of my y-axis. So to be a little mindful of positive, negative when you decide where your coordinate system is in these problems. That's one thing that you have to pay attention. You can decide where your coordinate system is, but then you have to be very careful about when you are in the positive side, when you're in the negative side, when you're in the positive, in x and y direction. All right. Question on this one. Nice. There are a few more problems on this. I'll post just for curvilinear path motion related to or solving curvilinear path problems using Cartesian coordinates. You can totally erase the first part if it makes you confused. Had nothing to do with the way we solved the problem. I was trying to start from scratch, but I realized that that's probably is more confusing. Let's just stick with the equations we already derived. So this is just, you don't even need to be concerned about that. That's how we solve the problem. Don't want you to get confused on those, with those. All right. So far so good, hopefully. Last thing I want to talk about, we have some time. So I want to start talking about the second way of dealing with motions on curvilinear path. So this Cartesian coordinate, using Cartesian coordinates to solve these problems, we define our coordinate system in a fixed spot, right? It's just we put it in somewhere and then we track the motion. Right? The other way of doing or solving these problems is instead of putting our xy coordinate or using Cartesian coordinate to follow the motion, we can use a different coordinate, a coordinate that is along the path of the motion. Right? We're talking about the curvilinear path. So instead of having an xy coordinate to study a curvilinear motion, it is on a specific path, we can use a coordinate system that is attached to the path. It's called tangent normal coordinate system. Basically, instead of xy, you have one axis that is tangent to the path and the other axis that is normal to the path. So let me, all right. So I'll put it under 2. Remember, first one was Cartesian coordinates. I think I used green for numbering. Quickly go back to double check so I'm consistent. We started with Cartesian coordinates. Yeah, so let's go with green 2. Call it tangent normal coordinate system. Tangent normal coordinates. Remember, we're still trying to study the same motion. Like motion on a curvilinear path. Path is not straight. Somehow it's curved in some direction. It can be any kind of path, as long as it's not straight. Fits into this category. But we're using a different coordinate system. So the motion is the same. We just want to study that using a different coordinate system. Let's put it this way. Put few sentences here. You can say, in this case, in this scenario, I would say, we specify the position of a point or of a particle. Remember, these are particles. We're talking about particles, but later on we'll expand this to rigid bodies. Of a particle by a coordinate measured by a coordinate measured, can say along the path of the motion. And express the velocity and acceleration in terms of, let's say, in terms of the normal component and tangent component to the path. So mathematically, what I'm trying to say is that, let's say we have a path like this. I have a particle. I'm following that particle, an object moving along a path. Right? Start from here. Now, if at one moment it's at this point, particle is at where it is at time t, pt. We show the particle with t, with p and t being the particle where it is at time t. At another moment, it's at p t plus delta t. It's some few moments later, few seconds, few minutes, few hours, or depending on what your time frame that delta t is. So previously, what we were saying was, well, I have a point O, right, some origin of my coordinate system, and I say, well, this is where P is at T, and this is where P is at T plus delta T. So I can represent those as RT, position at T plus delta T. And this is the motion on this path. And remember, we define velocity as dr dt, right? Change of position, change the position, or become basically displacement as dt. I can write it as mathematically, we can just write it as limit, right, minus r at t divided by delta t when delta t goes to 0, or we can just write it easily as delta r. If I define delta r as this change, right, let's define delta r. If I define delta r as going from here to here, this is my delta r. This is delta r, right? This is what we had. Let's say we have a Cartesian coordinate system, and we want to know how can we go from this Cartesian coordinate system to the coordinate system we're trying to introduce, tangent normal coordinate system. Now, position O, the position vector R, right, specifies the position of P related to a reference point, like this point O. This is a reference point right here. Now, what I do, I introduce a new measure, right? I say S, which we actually saw it when we were talking about motion on a straight line. I introduce this point, some O reference on the path, I call it O prime, and I say this is S. This is S. Basically, coordinate S measures P's position along the path relative to point O, O prime. So let me write it down here. Coordinate S, let's say measures P's position along the path relative to a point O prime, right? Some reference point on the path. This O prime is on the path. On the path. All right. So if that's S, now I can say, I can define delta S. Right? I can define delta S as this distance going from where the particle is at the initial of measurement, let's say t, and where it is at t plus delta t, and this time with respect to S. Right? That's my that's what I'm using as the coordinate instead of this fixed point of coordinate r. Okay, so let's see how can we connect these two. The definition of velocity, this should be a vector, and this whole defining the velocity using this new coordinate system. So I define what I will do to connect these two. I define a unit vector E that is in along with R. So if this is R, this is E. A couple of definitions going on there to just get this right. So E, this is unit vector E. What is unit vector E? E is, let's write it this way. E is the, let's put this, we introduce unit vector E to the point, right? That's basically the vector E is introduced to the point in the direction of delta R. Direction of delta R. So V, velocity as a vector, is limit, right, delta R over delta T when T goes to 0, E, right? Because it should be in the form of a vector. This is a vector. This is, keep it as a vector for now, as a vector. Now, as delta T goes to 0, delta R and delta S, look at the representation on the right. The green arrow and the pink arrow. Green arrow is a straight line from the moment T to moment T plus delta T. Pink, or I guess that's the color. Color, delta S vector, is along the path. So as delta T gets smaller and smaller, PT and PT plus delta T gets closer and closer, and delta R becomes the same as delta S, right? For very small distance, delta R and delta S, think about a curve, you know, we have a curve, the smaller we get on the curve, the smaller that piece becomes, or the closer it becomes to a straight line. So I can write this as limit delta S over delta T when delta T goes to 0. Well, delta S is a magnitude, so I have to introduce E here as to give it a sense of a vector. Right? So the smaller dt becomes, the closer delta S becomes to delta R. Now, dt is going to 0, meaning that at the limit, delta R and delta S are the same size, they have almost the same size. I only use E to represent the directionality because R is a vector, so S should have the same sense. So here, let's put it this way. When, also we can write it this way, delta E. Now here's what happens. When delta T approaches 0, you know, it's a limit. So it becomes a derivative. Delta S, delta T becomes ds dt. And E becomes tangent to the path. So we're going from Cartesian to normal tangent, or tangent normal coordinate system. So if I do that, this becomes V is V. Remember, we defined delta S or ds dt as V. Right? This is what we defined all the way at the beginning for a straight line motion, a straight line path. Right? If you had a straight line, we said S is where it is with respect to some origin O. Velocity was ds dt. So ds dt is V, and the vector is et. I'm representing it with et as the tangent. So this becomes et, which is basically ds dt et. This is one equation that you need to know. So the velocity of the particle, right, when it's passing or it's moving along a curved path, or it's a curvilinear motion, is ds dt s, change of s, which is measuring where this point is with respect to some origin or some reference point on the path, multiplied by the vector tangent to the path at any given time. Now, if we know velocity, right, we can actually find the acceleration. So acceleration becomes A is, well, it's a derivative with respect to time from velocity, dv dt. So d dt v et becomes d dt v et plus v d dt et. It's a multiplication. I'm taking derivative of v et, well, derivative of the first one multiplied by the second one plus derivative of the second one multiplied by the first one. Now dv dt et is this part is not really that unusual. The derivative with respect to velocity, right? The derivative of velocity with respect to time. The second part, we have to take derivative of a unit vector et. Now remember, this is the situation we are in. We are moving on a path like this. We have a vector t per tangent to the path, and this is, let's say, the angle at the moment is with respect to the horizon. So this is a tangent normal path. Obviously, this is tangent coordinate system. It's a tangent normal coordinate system. I introduced the normal part being in this direction. Well, it has to be in the same color. So this is En. It's supposed to be En. En. So now I have a coordinate system. Et is the tangent to the path. En is normal to the path. Now you might ask, why do I take the direction in this way? I'll give you an explanation. But basically, is acceleration is always expressed when we express it in this form. The unit vector En must be defined to the point towards the concave side of the path. That's why I define it this way instead of defining it in this way. Because the acceleration, the unit vector should be concave to the path, and that's why we take it always in that direction. Now, without proving, I'll just tell you this, that det dt, which is basically the second part of this equation right here, right, is d theta dt En. This is just, I'm giving you without proving that. You can take a look at your textbook if you want to go into details how to mathematically prove it. But this is a given. Right? Take it from me. So if you plug that in, then acceleration becomes dv dt et plus, right, v d theta dt en. This is a relationship for acceleration. So remember, we're going from Cartesian coordinate system to tangent normal coordinate system. And this coordinate system has two, well, it's represented by two unit vectors. Similar to I and J, we used to define Cartesian coordinate system. You're using ET and EN, tangent and normal, to define normal tangent coordinate system. ET is tangent to a path, EN is normal to a path. Now, direction of it, no, ET was obvious, the direction is normal, tangent to a path in this direction of the motion. So if you're going this way, it's tangent to a path in this direction, wherever the acceleration or the motion is going. Normal component is perpendicular to tangent. This is 90 degrees. It's not what I wanted to use. This is 90 degrees right there. And it's normal to the path. So if you follow the path, it's always these two. One is normal, tangent, one is normal. Now in this new coordinate system, the velocity is ds dt et, right? Wherever the particle is on the path with respect to time, you know, the change in its position in the tangent direction, that gives you velocity. Acceleration has two components. One in tangent direction, one is normal direction. Tangent direction is basically just the derivative with respect to time from velocity. Normal component is derivative with respect to time of theta, right? That theta creates the particle or the path creates with horizon. With respect to time, times v is velocity in normal direction. I'll continue this in the next class. So one thing we're going to add, so we're going to get another equation for acceleration, right? And we're going to get we're going to talk about the next special case, which is when the motion is on a circular path, right? I'll stop here. Just wanted to have enough time to get into details. But the gist of it, the story is, I'll start here and do review next class. But the story is we're going from Cartesian coordinates, which is some fixed point following the particle, to a coordinate that is on the path. Right? It's introduced, or it's defined by two unit vectors, similar to any coordinate system is defined by unit vectors. One is tangent to the path at any point the particle is. One is normal to a path. We represent the tangent one with ET, represent the normal one with EN. Similar to I and J, now we have ET and EN. Right? So we defined our velocity and acceleration in the new coordinate system. We'll get into more details about how the different variations of this equation and what is the special case for a circular motion, define a few things, and then we'll look at more examples for tangent normal coordinate system. I'll just stop here.